everyone. This video is going to explain how the input and outputs of a programmable logic controller, PLC, interact with the program code. One of the things that I found from teaching PLCs for the past 25 years is that new students to this topic have a difficult time understanding how the I/O interacts with the program code that we write. So in this video, I'm going to explain a way to understand how this code functions. What we're going to do in order to build or to understand this reaction, we are going to build a simple start-stop circuit where we know that the stop push button out in the field is a normally closed device, and these push buttons are going to be momentary. So stop push buttons are always normally closed out in the field. The start push button is always normally open in the field. So when we look at this particular circuit, when we know that there's power flow capable of flowing through this stop push button because it's closed. Now I'm assuming we know how to read ladder logic. If you don't, there's a lot of videos on YouTube that will teach you how to read ladder logic. When you press the start push button, this switch will close, and I'll have current flow through the two switches and energize CR, which is control relay. When CR's coil is energized, its contacts are going to change state. So the normally open contacts associated with CR are going to close, and the normally closed contacts associated with CR are going to open. So since I wired the normally open contacts of CR, when CR energizes, these contacts close. Now I have power flow through the stop switch, through the start switch, through the CR contact to CR. So that when I release the start push button, I will still have power flow through this closed set of contacts to hold the CR coil on. This is called a seal-in contact. I'm going to seal in the start push button. When you press the stop push button, it opens the circuit, current stops flowing, which means this coil gets de-energized, and when this gets de-energized, the contacts go back to their normal state, where the normally opens are open and the normally closed are closed. So when the stop push button gets released, now I have no current flow through the start, and I have no current flow through the control relay's normally open contact. So that's what we're going to build in the PLC. Now in the PLC, we can look at this as follows. Here's an input module, and I have a stop push button wired to an input on the input module. I have a start push button that's wired to the input point on an input module. In between the input module and the CPU or the processor module, there's this word. It's a binary word. It's called a variety of different things depending on what manufacturer you're talking about. But in general, we're going to call it an input image register, because it's going to contain the status of the input devices. In memory, we build the start-stop circuit that we had in the electromechanical world. And then we have an output module and I wired the CR coil to an output point, and in between the processor and the output module is an output image register, which is a binary word, which will contain the status of the output devices. Now, when we built this in the lab, what we did was we looked at my field devices, and if I go back to this drawing, we looked at the field devices and said, okay, I'm going to program this now in the PLC. And in the PLC, you said this should be normally closed. So we programmed it as a normally closed switch. Only to find out that when we finally downloaded and ran this program code, it didn't work the way we expected it to work. What I did was I have this program code running right now on an Allen Bradley Micro 820 PLC, where this over in this window is the ladder logic that we built in the lab that we were doing. So even though it graphically looks different than what you did in Studio 5000, it's the exact same logic. So this is what we ended up with. We ended up with a normally closed stop push button. And if you remember, this is called an examine open or examine if open. We had a normally open start push button. This is an examine close or examine on or examine if closed. We have a run control coil, which is our CR. We have a contact, a normally open, which has the same tag as our run control. And then we had a second rung that we're going to deal with after we talk about how this I/O interacts. And right now, this program is running. It's running because in this particular version of software, and this is the Allen Bradley or the Rockwell CCW, which is Connected Component Workbench, I see that there's a red line here and I've got power flow. I also have the tag monitor up, and we can see that the stop push button is a 1. So the stop push button in the field is closed because it's a binary 1. The start push button is not a 1. It's a 0. In this version of the software, these check boxes can be used to change the value. So if there's a check, it's a 1. If it's not checked, it's a 0. And we see that the tag name happens to be red, which also tells me that out in the field, that switch is a 1. But I have no power flow through this instruction. And that puzzled a lot of people. Wait a minute. The field device is closed. Why shouldn't the program instruction be closed? I can make it work. I can take the stop push button and make it a 0. And now you'll see, look at this. I have power flow here. And when I make the start push button a 1, I now have power flow through here. Run coil energizes, run control contacts close. When I release control from the start push button, you can see I still have power flow. However, the stop push button is a 1. So in order for this to work, I would have to continuously be holding the stop push button in. So why is this happening? That's going to be the question. Why is this happening? So let's take a look at why this is happening. First of all, I want you to understand that PLCs, when they were originally designed, were designed to be relay replacers. That's exactly what they are. They're relay replacers. So when we look at this circuit, and before we build the ladder logic in the PLC, let's take each one of these switches and say we're going to control relay coils with them. And then we're going to use the contacts off the relay coils to build the ladder logic. So I have a stop push button, which I wired to plus volts, and it's going to control CR1. So you'll see that CR1 is going to be energized because the stop push button is closed. And I wired the start push button so that it's controlling CR2. Well, the start push button is open. Therefore, CR2 is not energized. So I'm going to use the contacts from CR1 and from CR2 to build the ladder logic. Now, I have to know this status out here. In order to program PLC logic, you must know the status of the field devices. I'm going to repeat that. In order to build and program PLC ladder logic, you must know the status of the field devices. I need the first instruction or the first contact on my PLC start stop rung to be closed when nobody is pressing the stop push button. So if I look at the circuit right now, the stop push button is already closed. CR1 is energized. That means that the normally open contacts are closed and the normally closed contacts are open. And I showed that with the green on the normally opens and the non-green on the normally closed. So right now, the normally open contacts of CR1 are closed. So in order to get a closed contact in the PLC or in my ladder logic, I would have to wire the normally open contacts of CR1. So when I'm wiring this circuit using the relay contacts, in order for the stop contacts to be closed, knowing that the stop push button in the field is closed and CR1 is energized, knowing that the normally open contacts are closed and the normally closed contacts are open, I need to physically wire the normally open contacts. So I'll come over to here and I would wire in a normally open contact from CR1. Because I know that when I run this program or when I run this circuit, the normally open contacts of CR1 will be closed. To put the start push button in, again, I need to know the status of the field device. The field device in this case is normally open. The coil, CR2 in this case, is not energized. Therefore, the normally open contacts are open. The normally closed contacts are closed. I need the start switch or the start contact to be open. And therefore, I can wire the normally open contacts from CR2. So I will wire the normally open contacts of CR2. The relay coil, I'm just going to do another, I'm going to wire a third relay coil, which I didn't show here, but we're going to wire another relay coil. And I'll just call this CR3. I'll just make it CR. And I'll take a set of contacts from CR to fill in, or to seal in, my start contact. So this is CR. So right now, this is my stop switch, or my stop contacts, and this is my start contacts. So that now when I press the start push button, CR2 will energize. And when CR2 energizes, the normally open contacts will close. That will close these contacts. I will then have power flow through CR1, CR2 to turn on CR's coil, which will then close its normally open contacts, so that when I release it, I will have power flow through CR. Then when I press the stop push button, it de-energizes CR1. Therefore, the normally open contacts will open, or be open. The normally closed contacts will be closed, which says that CR1's contacts will open and break the power, so that CR de-energizes, CR opens. When I release the stop push button, even though these contacts change state, I will no longer have power flow. So I literally had to wire the normally open contacts from CR1, or that are the contacts that are controlling the stop push button relay. So let's go back to our ladder logic. And what I'm going to do is I'm going to go offline with this program. I'm going to disconnect, and then I'm going to change this contact, this instruction, to a normally open. And in this software, I can do that this way. Remember, if you're using another version of software, the way you do it in that software will probably be different. So now I have a normally open instruction, or an examine close. And I'm going to download this program again. Because this time, while the program is downloading, I'll just tell you that this time, this circuit should work the way you would expect it to work. And we're online. Let me bring up the ladder. You will see that the stop push button is still activated, which it should be. But this time, it is now closed and passing power. So that now if I press the start push button and then release it, I had power flow through the start, energizes the run control, seals it in, and now when I make the stop push button, press it, it opens, release it, it closes to de-energize. So, in PLC logic, you must know the status of the field device, and you have to know the status of what you want the instruction to be when nobody's operating the field device. So let's go back and look at that in this drawing. So here's this drawing again, and here's the ladder logic that's running in the program. Right now, if you look at this stop push button, I've got current flow. I've got current flow through the stop push button in the module and back out. That means that there is a binary 1 in this bit position. If you think of each one of those bits as a relay coil, that means that this stop push button is energizing this coil. And the coils the contacts associated with that coil are in their reverse states. Normally open contacts are closed. Normally closed contacts are open. Now that's not a relay coil, it's a bit in memory. But the bit is a 1 or on. And when the bit is a 1, any instruction that's programmed to it will be in the opposite state of the way it was programmed. Let me repeat that again. When the input image register has a 1 in a bit location, any instruction in the ladder or in the program code will be in its opposite state. The start push button is open. There is no current flow here, and it will have a 0. And with a 0 in that bit position, it says that the coil is not energized for that start push button. Therefore, the normally open contacts are open and the normally closed contacts are closed. And that's exactly what's happening. The start push button is open. So when you press the stop push button, that goes to a 0, they will open. When you press the start push button, this bit will go to a 1. The coil's energized. These contacts, or the start contacts, are going to close. I'll have power flow. CR closes. CR's contacts close. And when you release the start button and this goes back to a 0, the start button opens, but I will still have power flow through the CR button. I hope that explains to you how it interacts. The thing you need to remember is you must know the status of the field device in order to properly program the ladder logic. And what you're going to do is you're going to, based on the status of the field device, how do you want it to function in the ladder, and you can program it in the way you need it to program. So I hope that helped. We're going to do more of this because in the next part of this video, we're going to add some logic to it. And we're going to show you some other things that you need to be aware of. So again, I hope this really helped.